So I'm going to play around with these beakers again. And I got the first beaker. Let's put 50 degrees Celsius water in my first beaker. And 200 grams. I know that we always measure water in milliliters. I'm going to do it in grams because we're going to have to talk about masses. So I recognize that this is a little bit of a strange choice. We're going to say we have another 200 grams of water at 70 degrees Celsius. Then we put them together. I know this kind of looks like a chemical reaction. It's just a mixture, though. I put these things together as a mixture. Incidentally, when you're doing these kinds of things, FYI, water, one of the definitions of water is that 1 gram of water is equal to how many milliliters? Does anybody know? 1, yeah. That's a very convenient definition. Do you think it was on purpose?
Yes.
It 100% was. Yeah, so if you're somebody who's doing healthcare schism or HOSA or one of these sort of things, this is like a nice piece of trivia to know. Anybody doing that kind of thing? Yeah. Then another nice thing to know in that vein is that so that's specific for water. This is true for everything, though. Maybe I should say this. Everything, every liquid. So for you healthcare people, I'm sure you already know that 1 cc is short for what? This is something they use in medicine. Saline solution, you're going to give somebody so many cc's of a saline solution. What's a cc? Cubic centimeter. It's a cubic centimeter. So 1 cc is 1 cubic centimeter. Hear it all the time in medical shows. My mom was a nurse. Always talking about cc's of something or other. What's a cc in volume units? Anybody know what it translates into? Cubic centimeters equal to how many milliliters? Yeah? 1.
That's great.
Again, on purpose or on accident? On purpose, okay? So this is some nice stuff to just know in the background for vocabulary. I think I learned this for the first time when I was in grade 9. Miss Knight taught me that. But that's nice things to know for chemistry and for medicine. For us in physics, we can know it too. So when I put these things together, I'm going to get 400 grams of water. Now, if this is water, 400 grams of water also happens to be 400 milliliters, okay? Just because of that little nice thing about the definitions for the values. Now, which one of these 3 beakers, I'll review this again, which one of these 3 beakers has the lowest amount of heat in it? Lowest amount of heat. Yeah? First one, yeah, lowest heat. Without even figuring out what the temperature is of the third one, which one has the highest heat? Yeah? The third one. Yeah, this one has the highest heat. Remember, heat is the total kinetic energy of all the particles. Of course, if I wanted to figure out what the temperature is in this very special case for the third beaker, T final would be T1 plus T2 divided by 2. And I know that some people did this in their heads last time, but you probably could do this in your head this time. So we're talking 50 degrees Celsius plus 70 degrees Celsius divided by 2. What is it? Yeah, 60. This is a friendly one to do in your head. Okay? Now, this formula is a fine formula, but it's only, underline, only useful for identical substances. Yeah, substances with identical masses. So people say, well, why would you even bring up one that's so pigeonholed, like so specific? I'm bringing it up so that you recognize that this is the only time you can ever use this formula. It has to be identical masses and identical substances. How often do you think you actually mix the exact same amount of the exact same stuff with each other? Like basically never, right? So this is so specific as to be almost useless for us. Okay, it actually does work for water sometimes. Like if you wanted to cool down water, you could think this way. But unless you're adding equal amounts of water, it's not useful. Okay, so that's where we got to go with this next. We got to sort of like over the course of the next day or two, figure out how to deal with the fact that you're going to deal with different substances and different amounts of those substances. That's got to be a thing for us, okay? So I'm going to make a little bit of a statement here, a little bit of a written statement. The total thermal energy, this is the first law of thermodynamics. That should have had more of a dramatic intro, I suppose. The total thermal energy of a material in a, you know what? I think I want to do like, I got to carve off a little space for myself here. So I'm just going to put a little line there. Total thermal energy in a material in a closed system. And it's important that it's closed. We're not letting energy in and out. Is equal to the system's original thermal energy. Yeah, energy initial equals energy final. We could say if the system, and this actually I'll put it in brackets because it's not really a part of the first law of thermodynamics. It's just sort of a tack on that I want to add on there. If the system is open, I'll underline the word open to draw attention, energy may be lost or gained. By cooling or heating. And so we're talking about an energy exchange with the environment if the system is open. Think about like a brand name coffee mug or something like that. Think about your favorite brand name. Doesn't matter if it's Stanley or Yeti or Thermos brand. If the lid's not on there, it's going to be a less contained system, and energy is going to come and go, right? Like, I mean, I know for myself, if I fill up my coffee in my brand name coffee cup, it's going to stay hot. In fact, I almost burned my mouth this morning because I made my coffee at 7 o'clock and I didn't get around to taking my first sip till 8:30, and the lid was still on there. I know that this is a good almost closed system because I almost burned myself. That's a good coffee cup, right? I had to leave the lid off just so I could drink it a little bit, and I left the lid off. I should really finish it. It's getting cold now because it's an open system. Closed system is going to keep the same amount of energy the whole time, okay? I want to go over here. I want to say, you remember when we were talking about doing negative work on things from friction? This is kind of like that. When the change in heat energy is positive, so let me make sure right, if delta EH is positive, things get heated up. If delta EH is negative, there's my minus sign, things do what? Yeah, things cool down. So there's a couple little facts about the signage on heat energy. And then another little fact, I want to draw your attention to it again, only because you're going to see it in chemistry. I want to make sure it's really clear. If you see this in chemistry or if you see it with an online tutorial, I'm going to use delta EH for heat energy, but chemistry and many people online are going to use capital Q for heat energy as well, okay? Just know that means the same thing. And if you have a mom or a dad or an aunt or a cousin that's an engineer, there's a real good chance that if they're helping you with your homework, they're going to use capital Q. Just saying, okay? All right, so we have delta EH equals MC delta T. Look at that. It looks all sloppy. It took extra effort to make it sloppy. The equation editor would have made it neater. But I want you to notice that I want to pop off the page at you. Let's label this thing up. Delta T is the change in temperature. And here I am just giving this to you as like this magical equation. I didn't even derive it or anything. But I'm going to tell you, this is the amount of heat energy that changes, and this is the formula for it. But when the temperature changes, we're talking about how many degrees Celsius did it change. And when you see delta T, it means T2 minus T1, the final temperature minus the initial temperature. We've been saying this in words already, but delta EH is the amount of energy lost or gained. And I just mentioned a few moments ago that sometimes that energy is going to be positive if it heats up, sometimes it's going to be negative if it cools down. Now the units are going to be in joules. But let's think about this. When would it be negative? Can you see that it would be negative if T1 is a bigger value, T1 is a bigger value than T2? In other words, if T1 was 100 degrees and T2 was 20 degrees, it would be cooling down, and that would produce a negative value. If T2 was 100 degrees and T1 was 20 degrees, 100 minus 20 is positive 80. That would be a positive. And if you started at 20 and you heat it up to 80 or to 100 degrees, it would make sense that you're adding heat to this thing. So where does the positive and negative sign come from for delta EH? It comes from the temperature change, okay? Drawing attention to that. The M, this is the mass of the material. And this actually is a difference between chemistry and physics. In physics, we're going to use units of kilograms. Because molar masses are calculated in grams per mole, chemistry will use units that involve grams. That will not affect the concept at all, but it will affect some of the values a little bit, okay? So just letting you know that, again, same language, different accent. We're just saying the same thing in a slightly different way. We're going to use kilograms as our SI unit standard in physics. So we're being consistent through the entire course, okay? This C, though, this is the new thing. This is called the specific heat capacity. Specific heat capacity. This is a new concept for us, but I want to make sure that we know what it means. It is the specific amount of energy required to raise a specific substance I know I should have used particular substance to vary my words, but I want to really emphasize specificity here. For a specific substance by 1 degree Celsius or 1 Kelvin, because remember, 1 degree Celsius and 1 Kelvin is the same size. In terms of the units, now the units seem a little bit confusing. We're talking about how many joules it takes per kilogram per degree Celsius. So the units are joules per kilogram degree Celsius. Which seems like a really ugly unit. And I'm not going to lie, it is kind of an ugly unit, but it means something. How much energy it takes to raise 1 kilogram of a block of iron by 1 degree Celsius, if you like. That would be the specific heat capacity of iron. And so I have a list here, actually. Iron is one of the items. I have a list. And people say, well, do we have to memorize this list? Oh my gosh, no. This is an experimentally determined list of values, okay? Like people actually heated up iron, they heated up water, they heated up glass, and they figured this out, okay? And we can talk about how that would be done. We'll do an experiment to do with this, okay? But the specific heat capacity for water, C subscript W, is 4.18 times 10 to the power of 3. So that's 4,180. And then the units are joules per kilogram degree Celsius. Specific heat capacity for glass, crown glass, is 8.40 times 10 to the power of 2 joules per kilogram degree Celsius. And the specific heat capacity for iron, that's C subscript I, is 4.50 times 10 to the power of 2 joules per kilogram degree Celsius. Now, when we do our cooking, we will often use glass vessels and iron vessels, like pans or like a Pyrex dish or something like that for making a pie or something. It turns out that those things don't require a lot of joules to heat them up by a degree Celsius. You see what I mean? Look at water. Can you see that it's a whole order of magnitude more energy? Per kilogram of stuff, water takes 10 times more energy to heat it up by a degree Celsius. A kilogram of water takes 10 times more energy to raise it by a degree Celsius than a kilogram of iron. And people say, oh, a watched pot never boils. You heard that expression? What it means is it takes a long time to boil water. So don't sit there watching it. Go do some other things while you wait for the water to boil, and then add your noodles and your rice afterwards or something like that, okay? A watched pot never boils. But really what we know is that it takes 10 times more energy to heat up water than it does to heat up the pot itself, which is made out of metal, right? That's actually a good thing. It's good for us because we're mostly made out of water. It means that since we're mostly made out of water, it's tough to make us overheat. Yeah, we can evaporate water too. That's a different thing. Changes of state. We're going to talk about that in the future. But this idea of the lake effect, this fact that water holds on to energy so well, means that water takes a long time to release heat. A long time to release heat. Because it holds on to a lot of heat. Due to the fact that it has a 10 to the power of 1 factor of capacity difference. Well, capacity difference relative to what? It's got to be relative to something. You guys know that sand is mostly silica. Glass can be formed from fire-blasted sand. Would you believe that the water at the beach has 10 times more heat capacity than the beach does? Which is why if you go for a walk on a tropical beach, maybe you get to go for a holiday at a tropical beach, or maybe you just go down to the Ontario beaches in the summer. What you'll notice is after the sun goes down, the sand cools down in a hurry. During the day, you go down to the beach during a sunny day, doesn't it burn your feet? Yeah. It's true, right? The surface sand heats up really quickly, burn your feet. The water, on the other hand, does not get up to temperature like that. It just doesn't. It takes 10 times more heat to raise the temperature of water. The sand, much like glass, heats up in a hurry. It doesn't take a lot. Water takes a long time to heat up. And therefore absorbs energy for a long period of time. As a result, we can say, therefore, there's a temperature lag. There's a seasonal temperature lag even daily temperature lag. Around water bodies. And so if I'm out in the countryside, away from a lake, away from a large body of water, when the sun goes down, it gets cool in a hurry. If I'm right beside a huge body of water, when the temperature goes down, I'm actually still sitting beside this body of water that's been heating up all day long. It's like I got a giant hot water bottle right beside me, and it's still radiating heat off of it. It's going to lose energy all night long. And to a more extreme effect, that happens in the winter. That large body of water holds on to heat, and it radiates the heat out into the surrounding environment for a couple of months afterwards. By the time the winter gets to February, it's pretty much depleted. And then if you're somebody who likes to go ice fishing or something like that, for this reason, because of that lag time, I do like to go ice fishing. I like to go with my cousins and go ice fishing. We typically don't get to go ice fishing till around February, because that's when I mean, we don't talk about the science of it. We just know when the time is to get together. And my cousin likes to build a little ice hut. He puts it on skis. He pulls it out with a snowmobile. We have a real nice time. But we know because of that lag time, it takes a little while sometimes, especially in southern regions like where we are right now. If you're going to go ice fishing at all, you got to wait until the heat has already dissipated from the lakes. It's fun to think about the science of it. It's more fun to go fishing and hang out with your cousins. Yep.